When we're given expressions, sometimes we have limitations as to what values we can put in for our variables. So we're going to be talking about the domain of an expression. Those are all the values for which that expression is going to be defined. So here we have 2x plus 3 inside a radical. So 2x plus 3 is the radicand. So you have a radical sign and you have a radicand inside that radical. Okay, sometimes there's a number there, that's the index. When the index is even indexes require positive radicands. Quite simply, that's how it works. So we need the radicand, when we say positive radicands, we need the radicand to be greater than or equal to 0. Positive radicands or 0. So non-negative. Let's say that. Let's change that to non-negative. That's a much better way to say it. Rather than positive or 0, just non-negative. Non-negative radicands. So that would, this non-negative radicands algebraically transfers to this. Okay. So how did they get the solution set? How are they getting this solution set of negative 3/2 to positive infinity for all the numbers that define that expression? Well, they did exactly what we just said. They took the radicand and set it greater than or equal to 0 so that it was non-negative, and then they solved. So when we solve linear inequalities, very simple compared to those quadratic or even cubic inequalities. So this is just a linear inequality. X is greater than or equal to negative 3/2. Negative 3/2 is 1.5. So in interval notation, negative 3/2 to infinity is how we would define the domain. Now, one more thing to think about. I'm going to put this in red because it's crucial. So radicands with an even index has to be greater than or equal to 0. If you've got a denominator, remember that denominators cannot equal 0. And if you have a radicand in the denominator, then the radicand can only be greater than 0. It cannot equal 0 because of the blue exception. Denominators cannot equal 0. So let's find the domain of each expression. Keep that in mind. We're talking about radicands with an even index. Denominators cannot equal 0. A radicand in the denominator, then the radicand has to be greater than 0. Or cannot equal 0 if we have an odd index. Okay, so see if you can try these. You've done these probably a lot in the past, so we're going to see if you can try them. I'm going to work them out, so if you want to just keep this rolling, you are more than welcome to do that. We've got our first one, 3x minus 2 is greater than 0. 3x minus 2 is our radicand. Going to set it greater than or equal to 0. 3x minus 2 is greater than or equal to 0. Add the 2, divide by 3, and I get x is greater than or equal to 2/3. So in interval notation, 2/3 to infinity, done. Here we have an even index, but a denominator. So remember, denominators cannot equal 0, therefore we're talking about the radicand in the denominator, 3x minus 2, can only be greater than 0. Add the 2, divide by 3, and we get x is greater than 2/3, which does not include the 2/3, so now we have parentheses. Excellent. Now here we have the cubed root of 9x plus 1. This cubed root is an odd index. An odd index, as you'll recall from previous algebra classes, means that your radicands can be positive and negative. Therefore, all real numbers work. And the reason all real numbers work is not only because you've got the odd index, but because you don't have that radical in the denominator. So all real numbers work. This is one way to write all real numbers. Okay. In interval notation, negative infinity to positive infinity is another way. But this notation right here, very important that you know what that means, so that if you see it on a test, you know that that means all real numbers. Okay, let's try this real quick, and we'll close it up here, find the domain of each one of these expressions, and I will quickly provide you the answers. So make sure you press pause so that you can work them out. 2 to infinity with a bracket on 2. 2 to infinity with a parenthesis on 2. And again, all real numbers, or negative infinity to positive infinity.